I'm excited to show you a way around repeated integration by parts. It's beautiful, but it only works on if you have a P part as your U choice. That's the bummer. It is so great. This tool is fantastic, but it only works in a very narrow situation where you're doing something that starts with a P as your choice. You can't do it if you're starting with an L. You can't do it if you're starting with an I. You can't do it if you're starting with an E or a T. It only works if you're starting with a P. Okay? So it's a great one. Some years I don't even show it to people. Just kind of depends on the group of kids and what, how we're doing. But I am showing you guys, so. All right. Okay. I think I'm going to skip this one because we've done it a couple times. This is what kind of a combination? What would you start with here? The E, right? You start with the E part. And this is doubly cyclic, so E is cyclic and cosine is cyclic. So this is the same as what we were just doing. If you have a double cycle, you're going to have to do it twice and then pull the integral to the other side and match it all up. So I'm going to skip this one because I feel like we've done it enough times in your homework. Okay? So go to the, I guess it's slide, is it 19 on your notes? Yeah. Okay. So in this example, we get to start with a P as our polynomial choice. Okay? This would require 2 rounds of integration by parts because it starts with an x squared. But there's another way to arrange your tables. So let me show you how that goes. So we're going to start with our x squared here and our e to the x dx, which would start with our normal position. And then what would be the grid underneath that? 2x. And then the other one would be e to the x. Okay? And then if we would proceed as normal, if we were making another grid, I'll just do it over here. Our second grid would start with 2x and e to the x. So it starts where the other one left off. And then you do it again. And you get 2 and you get e to the x. Okay? And then if I were to do a third integration by parts, it would pick up where the other one left off. And then you would do it again, and then what would you get? 0, and still e to the x. Okay? So e to the x is going to stay e to the x no matter what, but the changes are happening in the other one. So rather than doing all these separate grids, we just sort of make them into, well, okay, I'm going to start over. I'm going to start again. And then I'm going to start with the 2x e to the x and do the derivative of that as 2, and e to the x is going to stay the same. And then I'm going to do it again. And then 2 goes to 0, and e to the x stays the same again. All right, when you do your combinations, we always start with the diagonal. So we're going to have all these diagonal, if we were over here, we'd have this diagonal combination, and if we were in this one, we'd have this diagonal combination. So we're going to have all the diagonal combinations going down our grids like this. But what other combinations do we need? The horizontal ones. Okay, so we need a horizontal combination, and another horizontal combination, and another horizontal combination. All right, when we put everything together, okay, we start with the first diagonal combination. So it's going to equal. The first diagonal combination is going to be x squared times e. E to the x, sorry, just forgot the, okay. And then we have minus, because that's what comes next. And we can skip to the next diagonal combination. We're going to skip over the horizontals. And we'll get 2 x e to the x. I should put parentheses, I apologize. And then minus the next diagonal combination, which would be 2 e to the x, minus the final combination, which is the last horizontal one, which would be 0 with e to the x. And then we close out all our parentheses. Kaboom, kaboom. So what do we have to do with all of our negatives? Distribute them. And then what do we add on the very end?
Plus C.
Plus C. And then we're done.
So no horizontal.
Only the last one. You can skip right over. Okay, so we get x squared e to the x minus 2x e to the x. And then we have to distribute our negative, which is going to give me plus 2 e to the x. And then we distribute our negative again, but I just end up with 0 plus C. El fin. Okay, done. Isn't that beautiful?
Yes.
It is. It is gorgeous. It's lovely. Okay. The reason why you have to start with a P, the P part has to start first, is no matter high the polynomial, eventually, what will that polynomial get to all the way you do your derivatives?
0.
Yes, they will always get to 0. No other functions will do that. So you have to get down to the point where you're at a 0. Okay? So this is called tabular integration because we're making a table. Yeah?
What do you mean by the polynomial go to 0?
All the derivatives. So like x squared turned into 2x, 2x turned into 2, 2 turned into 0. Because every polynomial will do that. Because every time you lower the polynomial down a degree, down another degree, you finally and always end up with 0. Okay? All right, let's try another one. Here we go. If you were doing this the normal way, looking at the degree of the polynomial, how many normal rounds of integration by parts would it take you? It would take you 4. But if we do it as a table, because we have a P to start with, so I'm going to start with x to the 4th and e to the negative x. All right, so we just work our table all the way down till eventually we get to 0. So this would be 4x cubed. And then the antiderivative on the other side is negative e to the negative x. And then we'll do the next round, one derivative and one antiderivative. So 12x squared and positive e to the negative x. And then one derivative and one antiderivative, so 24x and negative e to the negative x. And then 24, one derivative and one antiderivative. And then finally, one derivative and one antiderivative. So all your combinations are going to go like this. So we're going to have a diagonal combination, and then the last one would be a horizontal combination. But what's going to happen to every horizontal combination?
0.
Why?
Because
Because the polynomial got to 0. So okay. And then here's another good way, a quicker way to remember how to distribute all of your subtraction signs, okay? The first diagonal combination always starts positive. So we're going to have, well, it always starts as it is. So x to the 4th and negative e to the x, so we get negative x to the 4th e to the negative x. The next combination is going to come after one subtraction sign. So I usually put my subtraction sign right there as a reminder that that's going to be subtracting the next one. So then I get a negative 4x cubed e to the negative x. The next diagonal combination is behind its own negative sign, but it's also behind the negative sign that was before. So how many negative signs are in front of it? 2. So there are 2 of them in front of it, which is eventually going to turn into a plus. And then the combination that starts with 24, how many negative signs are there in front of it? 3. So there are 3 of them. And the next one's going to have 4 negative signs in front of it. So if you keep track, and the final one is going to have 5 negative signs in front of it. Now I don't need all of them, because all of the ones that have an even number is going to be positive. So then what I usually do is now that I've kind of thought about that, I don't need those because 2 negatives make a positive. I don't need 3 of them, I just need 1 of them because that'll be a negative. I don't need any of these because 4 negatives make a positive, and I really only need 1 of those because 1 negative. So it's like alternating. All right, so then let's finish all of our diagonal combinations. So I did the first 2. My next one's going to start with what coefficient?
Negative.
Yeah, but what coefficient? 12, right? So it's going to be negative 12 x squared e to the negative x. The next one that has the 24 in it will also be negative 24x e to the negative x. Second to last one, which has the 24 in it, is going to be negative 24 e to the negative x. And the last one is going to be 0 e to the negative x plus c. So that's all the combinations. So what do you notice about every single term? What could we take out? I could take out e to the negative x. What else? A negative sign. Okay, I could take out a negative sign as well. And we know that this one has a 0 in it, so it's gone. So the classy way to write this is negative e to the negative x. So you're taking that out of every term, take the negative away, and take the e to the negative x, which leaves you with positive x to the all positive terms. 4x cubed, 12x squared, 24x, 24, and then plus c on the end. So that's the classy way to write your answer. Pull the negative out, pull the e term out, and then leave yourself with all positive terms as a polynomial of degree 4. How do you check your answer? Undo the whole thing. Take the derivative, I've used the product rule to take the derivative. Yeah.
If you distribute all the negatives, then isn't every single one of those values negatives, and then we just determine that only half of them are?
Only half of them are negative out here, but you have to remember there's also negatives that are here, which are causing those other terms to be negative.
Oh, okay.
Because not only are we alternating in the left-hand side, we're also alternating in the e side.
Yeah.
That was alternating also.
I forgot about the right side.
Yeah, the right side's got its own negative signs. All right, let's try another one. Does it work with trig? It sure does, as long as you start with a p. Okay, and it doesn't work with an L, doesn't work with logs, it doesn't work with inverse. It only works if you can start with a p. Okay, so we'll start with a p. So we're going to start with x cubed. And then we're going to have sine 2x. And what you'll have to watch here is your chain rule. Okay, so one derivative and one antiderivative. Okay, so Nathan Deere, can you give me the next entries? One derivative, one antiderivative.
3x squared and then negative 1/2 cosine 2x.
Good job. Okay, he did one derivative, one antiderivative. Okay, Carla, you want to try the next one? One derivative, one antiderivative.
6x.
Yep.
And then
Okay, so we keep our 1/2, yeah?
Sine 2x
Okay, and then, but we still need another chain rule.
times 2.
Not times, we're doing antiderivative.
Oh, that's another one.
Yeah, so then we're gonna multiply by another 1/2. So you can write it like this if you want to, but I would probably lean towards just going ahead and making that a 1/4. Okay, Nathan S., get us the next row. One derivative, one antiderivative.
6 and 1/8 cosine 2x.
Okay, and then 1/8, because we've got another chain rule going on, so that'll be cosine 2x. All right, David, finish us off. Take us home.
0.
Is that right?
Yeah.
Okay, what's wrong? We're missing something. Go ahead, Andre.
Oh, well, I was gonna say, isn't there supposed to be a negative from the 1/4?
Yeah, we need that. Okay, then we've got positive. Okay, now we're right. Because we've got to have 2 negatives in the cycle to complete. Okay, David, sorry. We started to interrupt you. Now you can finish us off.
0.
Uh-huh.
And 1/16 sine 2x.
Good job. Okay, awesome. So now we know we're done. We're going to go back and do all these combinations here. And we're going to have every other one get an extra negative sign for all the distributing of the negatives. Okay, so then we can just put it all together. All right, so Sam, start us out. First combination.
Negative x cubed over 2 cosine 2x.
Okay, I like to just, if you don't mind, 1/2 x cubed cos 2x. Okay, great. All right, Brandon, next combination.
And then negative 3x squared times negative 1/4 sine.
Okay, so how can I say that better?
3/4 x squared sine x.
Is it gonna be positive or negative?
Positive.
Okay, good. Positive 3/4 x squared sine 2x. Okay, Matthew, take over.
Okay. 3/4x.
Positive or
cosine
negative?
2x, it'll be positive.
Okay, plus 3/4.
Yeah, cosine 2x.
Do I need an x in there?
Yes.
Okay, 3/4 x
3/4 x cosine.
cosine 2x. Okay, good job. All right, Ian.
That will be 1/3.
Almost. That would be if 18 was the denominator.
Oh, 8/3 or 3/8.
Okay, positive or negative?
Negative.
Okay. Negative 3/8 sine 2x plus c. Okay, so can you imagine on multiple choice how many different combinations of like negatives and positives there could be, right? You miss one negative and you pick the wrong multiple choice one. Now, a more elegant, classy way to write this, you will often see this written this way. You'll see the cosine terms pulled out from negative 1/2 x cubed and 3/4 x. In fact, I could even pull out something, something more than just from the cosine terms. What else could I pull out? A half and an x. So you might also see this with it written this way. From those terms, I'm gonna pull out a half, I'm gonna pull out an x, and I'm gonna pull out a cos 2x. That would leave them with a negative x squared plus 3/2. And then from the sine terms, you could pull out a 3/4. And that would leave you with x squared minus 1/2 plus c. So that is another way you might see that answer, where it's partially factored, not fully factored, but partially factored according to the trig terms. You might see that. Okay? That